Hello. So today I'll be showing you how you could get some fractured soft body simulations in Houdini, and we'll be using Vellum for the soft body simulations, and I'll show you how you could import it to Cinema 4D, and we'll assign some materials over there and make it ready for rendering. So let's get started. So to get started off with, we'll be using this pumpkin model from the intro. And what we'll do with this is that we'll be fracturing it using a boolean so that we can get individual pieces to simulate. And before simulating, what we'll do is that we'll clean up the mesh a bit and we'll convert it into a low poly object so that it can simulate faster. And we'll be adding some custom forces so that our pumpkin can explode. And we'll be building some constraints so that we can determine which pieces stay together and which pieces don't. And after setting up all this, we'll be using Vellum for simulation. And after we'll simulate it, since we are using a low poly proxy mesh, what we'll be doing is that we'll be reprojecting the high poly mesh onto our proxy mesh so that we can get a higher quality result that we can use for rendering. So with that out of the way, let's try and replicate this in Houdini. Okay, so let's go ahead and add a GeoNode and we'll dive in. We'll add in an Alembic for importing our animation. Now I have made this animation before in Cinema 4D, so I'm just going to be importing that. So I'll add in a time shift, and what we can do with the time shift is we can right click on the frame here, we can right click and delete channel, and using this we can middle click and control the starting frame range, the starting frame of our animation. So let me just choose a frame like let's say 60, it doesn't matter. I'm just going to choose a frame that on which we can simulate on, and now I'll convert it to a polygonal mesh using a convert node. So if I go into the geometry spreadsheet, we can see there's only one point attribute, and same goes with the vertex and the primitive attributes. So that's because right now the Alembic is being imported as just one point. If I just enable the dot, we can see that there's just a single dot there. So we need to convert this Alembic into a polygonal mesh so that we can work with the simulation. So I'll connect that to the convert node and make sure the convert to is set to polygon. That's set to polygon by default. So now we can see that we have our geometry, and we'll move to the next step, that is fracturing. Okay, so now let's fracture our object so that we get individual pieces. So for that, I'll add in a grid and I'll add in a circle. Now let me visualize that. Let me make sure the primitive type is set to polygon so that we are dealing with the polygonal mesh. And I'll add in a copy to point node so that we can copy our grids to the points on each circle over here. Each point on the circle. You can see that it's not really aligned in the correct order. So make sure you play around with the circle orientation. So I want the grids to be facing up like this. And also we can see that the grids are just being aligned on the Y axis. What I want to have is, if I just visualize the circle, I want the point normals to face outwards from the origin. Right now they're all facing down. So to fix that, let me add an attribute triangle, and I'll add in this simple expression at n equal to at p. And what that does is that it's just assigning the value of the position on each point to the normals. So if I just enable that, we can see all of the points normals face outwards. So now if I go back into the copy to point node, all the planes will be aligned to that normal direction. Right now they're not facing the exact way I wanted them to. So make sure in the orientation, just choose the correct axes. I'm just going to be setting up the grid so that it works properly with the boolean once we do that. And I have already done this beforehand, so I know what values work best for me. You might have to play around with the settings. Okay, I think I'm pretty happy with that. So now we'll add in a boolean node so that we can fracture the geometry. And in the geometry A, we'll connect the animation that we have, and in the geometry B, we'll connect the grids that we have generated. And in the boolean node, make sure the set B is set to surface, since grids are just two-dimensional. They're just flat surfaces, so they don't have much volume in them. So we treat them as surface. So make sure the treat as is set to surface in the B channel. And what we'll do is we'll change the operation type to shatter. You can see the difference between the original mesh and the fractured mesh. It gives us that line. Now in the detriangulate, you can either choose to set it as all polygons, but what I recommend is since we are going to be simulating this, we don't want n-gons, and what the Boolean operation does is that it's going to be generating a lot of n-gons all over the place, since it's just fracturing it without cleaning up the mesh. So let's just change that to either unchanged polygons. So we can see that it generates triangles where depending on the intersections, or we can change it to no polygons so that all of the polygons get triangulated. Now I'll just be leaving this as no polygons. It doesn't really matter because we are going to be using this as a proxy mesh for our simulation, and later we'll be reprojecting this onto a higher poly mesh, so it doesn't really matter. And the good thing is simulation wise it will be more accurate and give us less issues. Okay, so now that we have generated all the pieces, let's add an assemble node. So this will help us identify these individual pieces and the points that belong to them. This will come in later. This will come in handy later on once we want to reproject the high poly mesh to our proxy mesh. So let me go ahead and connect that to the Boolean, and I'll uncheck that. We only want to be generating the piece values. So you can see that it generates this name attribute, and it contains all these piece numbers. So all these points that have the piece number 0 are under one piece group, and you can see that we have a total of 19 pieces. So I can visualize that by adding a color node, and you can better understand what it does. So you can see that all these points belong to individual pieces. So what we can do is that we can delete this prefix so that it only gives us the integer numbers, and that's fine. We don't need the prefix right now. Or what we can do is that we can uncheck create name attributes, and we can just enable piece attribute, and that will give us the piece attribute under the fracture class, and we can change that name using this tab over here. We can change it to any name we like. So I'll just change that to name, and you can see it does the same thing. So you can choose whichever one you want. So I'll stick with this. Okay, so now let's simulate the mesh. So I just want to give you an example of what will happen if we don't clean up our mesh and optimize it even more. So for that, I'll just add in a Vellum strut soft body. Now this is just a preset made up of two Vellum constraints. We can replicate this preset by just adding a Vellum constraint and just changing the constraint type over here. But I'll just be using this preset since it's already available, and it's a fast start. I'll just connect that to the assemble node, and I'll add in a Vellum solver. So I'm not going to be going over these parameters in depth. These are all pretty self-explanatory. The most important ones that you might have to play around is with under the Vellum cloth, the stiffness and the bend stiffness, also the damping ratio of each of them. And in the Vellum struts, you might have to play around with the stiffness and the stiffness of the stretch and the dampening ratio. So if I just allow it to play as it is without any change, let's just see what happens. And before playing, I'll just add in a grid so that it can fall onto. And now let's just play it. And so here you can see that it's not really simulating very well. We have a lot of issues and intersecting geometry. Also, we have some weird forces that pull the pumpkin inside rather than just letting it flop to the ground. So this is not a really clean and a nice looking simulation. So what we can do to fix this is that we need to optimize the mesh even more. Okay, so now let's optimize our mesh. So for optimization, we can add in a for each primitive node first. So first off, let's add in a remesh node. Actually, before that, let me go into the for each end node and enable the piece attribute. And if you remember, in the geometry spreadsheet, we have the piece attribute called name that we have generated from our assemble node. So we can enter that into the piece attribute, and we can enter it name. And let's add in a remesh node. And using this remesh node, we can reduce the total number of polygons that we have on our mesh. And this will greatly improve our simulation time since we are dealing with a lower resolution proxy mesh. So let me type in the value 0.08 for my use case. And next up, let's add in a clean node. So Boolean usually produces some bad topology. It will give us open surfaces, duplicate points on top of each other, and there will be a lot of unfused points also. So what we can do to fix that to an extent is we can add in a clean node, and in the clean node we can enable consolidate points and fix overlap. So what are polygons that are overlapping with each other, that will get fixed, and the consolidate points will basically just merge 2 points that are on each position into one. So that's done, and let's add in a final node, that is the fuse. So this will also close up our open surfaces if we have any, and it will also basically consolidate the points like in the clean node. So we can choose the snap distance, make sure that's set to pretty low, because if you set it high, too high, it starts to fuse unnecessary surfaces, like you can see. And the great thing about this is that since we are using a for each loop, it will only be affecting the individual pieces. So it will not be fusing between the pieces, it will only be sticking to the their own pieces. So in that way we don't have to worry about pieces being fused together or something like that. So we can choose a snap distance of something low. So for my case I'll be using something as 0.02, and we can also see that if I middle click on the assemble node before we optimized anything, we have a total number of primitives that is 30,000, and once we optimize it we have around just 11,000. So that's a pretty good start. Let's see what happens if we simulate it now. So as you can see, the simulation is much stable right now and more clean, and we have a lot of less janky movements and unnecessary issues. So we fixed almost all of the optimization issues that we had. So now let's move on to adding some forces. So let's say the parts on the bottom of the pumpkin, I want them to be intact, and I want them to stay together, and whatever that is on the top, I want them to kind of separate when they explode. So for that, let me go up and we'll add in the forces before the optimize and the simulation. So let me add in a point warp, and I'll be making a gradient based on the y axis. So let me add in a vector to float, and we'll be taking the point position from the p channel, and I'll feed that into the vector, and I'll only be taking the float value 2, so that is the y channel. So the first value is x, the second is y, and the third is z. So I'll only be taking the second value, and I'll feed that into a ramp, and I'll plug that into the color channel for the output. Now you can see that we already get that gradient from black to white. We can also add in a multiply node, and using this multiply we can control the strength of the ramp, and I'll add in a constant so that we can multiply it with something, and I'll change it to let it be a float, and I'll middle click on the input 2 and promote parameter so that we can control the multiply node from the SOP level. So in the input number we can change that to 1 for now, and can play around with the ramp. So let's say whatever is white, let me invert this gradient first. So let's say whatever is white, I want the pieces to stay intact, and whatever is black, I want them to kind of be free and explode and separate from each other. So I'll just play around with the gradients. Okay, so now that our gradient is done, let me just keep that aside for now, and we'll add an attribute triangle. And with this we can set the explosion force basically. So our pumpkin will be exploding outwards. So for that, let me also add in a normal node so that we can get some normals on our points. And if I just enable the normal visualization, change the add normals to points, we can see that we get some point normals now. And in the attribute triangle, what I'll be doing is that I'll be setting up a force that will explode our pumpkin outwards. Basically, there will be a force exerting on the pumpkin that will make it explode and kind of go outwards. So for that, I'll add in this expression at v. V is for velocity, and I'll give it a velocity of at n, and I'll multiply that with something of a higher number such as 100. So basically what we just did is that the velocity channel will inherit the direction from our normals, and that was and that you can see over here, these are our normals, and we'll be multiplying that with the magnitude of 100. So we can control the strength of the velocity using this multiplication number. So let's just play the simulation now and see what happens. So you can see that now our pumpkin is exploding outwards, and it's all working pretty well. but right now it's exploding all the pieces. I want the pieces to be sticking together on the bottom, and I only want to be exploding the top pieces. So for that, I'll add in a vellum constraint, and I'll plug that after the vellum strut and the vellum cloth. And what I'll choose for the constraint type is that I'll choose glue. And with this glue constraint, we can control which pieces can stay together and which pieces can go free. So if I just play it as it is without any change, we can see that our pumpkin explodes, but all the pieces kind of stay together intact. So none of them end up exploding. So what we need to do is that and also we can control the stiffness and the dampening ratio of the constraints. But what we are mostly interested is in this tab over here, that's called breaking. And right now we can see this threshold value is disabled. So it means that all the pieces will be constrained together using the glue constraint. So once we enable this, the glues will start breaking depending on the force that will cross the threshold value that we have set over here. By default, it's set to 0.1. Let's just set it to 0.1 as it is, and we'll hit play and see what happens. So you can see the top part has already exploded, and the other parts stay intact. So using this threshold value, we can define which pieces stay together depending on how much force is being applied on those particular points. So we want to have more control over the threshold. So what we can do is that we can enable scale by attribute, and using this attribute we can control where the glue constraints break basically. So using the gradient and the help of the breaking threshold, we can control that. So I'll just copy this and I'll go back to the attribute wrangle and I'll give the expression at. I'll paste that break threshold scale. Now it doesn't necessarily have to be this exact name. We can change this name whatever we like by changing the name over here. But for now I'll just keep it as it is. And I'll just type in F at CD. And now let's just hit play and see what happens. So there you can see that whatever is black, it's kind of separating from the rest of the mesh, and whatever is white, that's being intact. Okay, so to deform the high poly mesh, we'll be using something called as a point deform. That's what we generally use. And it has 3 inputs as you can see here. So the first input is the mesh to deform. So we'll plug that into the assemble node. That's what we want to deform. So this will be our high poly mesh. And in the third node over here, the last one, it says deform point lattice. And this is the deformed mesh that we want to reference so that it will affect our high poly mesh. Now I'll plug that into the vellum solver since we want to reference the simulation. And for the rest point lattice, it just basically needs a single still frame of our proxy mesh. So for that, I'll be using the output from the for each end node, since the output from here looks the exact same as the vellum solver, so that won't be an issue. Now let's just play this and see what happens. As you can see, it creates these ugly looking stretched primitives, and the reason that happens is because right now our pieces are too close to each other, as you can see, generated by these intersected lines using that boolean. So the point deform can't really figure out which point belongs to which piece. So it tries to deform everything at once. So that's why you get that stretched polygons. So what we need to do right now is that we need to isolate the point deform to deform on a each piece basis. So for that, let's add in a for each primitive node. And I'll just get rid of these connections so that we can start fresh. And the first thing I'll do is that I'll put this point deform inside the for each loop over here, like that. And we need to set up the for each end node. So since we are going to be using the input from the assemble node, it already knows that the pieces have been generated. We just need to refer them. So in the for each end node, we just need to enable the piece attribute. And as we know, our piece attribute in the geometry spreadsheet is called as name, and it's stored in the primitive section. So make sure in the for each end node, the piece element is set to primitives and the piece attribute is called as name. And we'll just plug that into the assemble node first of all. Now to isolate the deformation on each piece so that the point deform only searches for points to their respective pieces, what you need to do is we'll add an attribute wrangle, and we'll need 2 of those. one for the rest point lattice and one for the deformed point lattice. I'll just copy paste the same exact attribute triangle. And what we'll do is that let's get rid of that connection. For the first input, that is the mesh to deform, I'll be connecting the input from the for each begin, and that's the same input that's coming from the assemble node. So that will be going into the point deform, and the second input will plug in the attribute triangle. Let's call this rest, and we'll call this deform so that we can understand better. And for the mesh to deform, that is the deformed point lattice, we'll add in the third attribute triangle over here. Okay, now we want to import the rest point lattice and the deformed point lattice from our simulation. So for the deformed point lattice, what I'll be doing is I'll be importing the output from the Vellum simulation. I'll just drag and drop that to the default input node over here. And for the first input, I'll refer to the our for each begin node. And I'll do the same for the rest point lattice. And for that, I'll plug in the input from the for each end node. And I'll connect the output from the for each begin node to the first input of our rest. And also one thing, we want to convert the piece. We want to convert the piece attribute that's been coming into this section over here to points. Right now, as we know, they're stored in the primitive attributes. So we want to convert them, want to basically promote them to the point level. Now, the reason we do that is because it, for some reason, works well when it's in the point level. So the way we do that is using an attribute promote, and we'll be using this both for the Vellum solver and for the rest point lattice. So I'll just override that, and in the attribute promote, let's convert it from the primitive, since our piece attribute was stored in the primitive section, and the new class we'll set it as point for the original name, because that's what our piece attribute is called. And also we'll convert it into a new name. We'll just say name underscore p so that we can know it's in the point level. And this is where it will get a bit tricky. So basically what we are trying to do is that we'll be deleting all the pieces except one, and we'll keep this one piece for the point deform to calculate and deform. So the way we do that is we can type this expression if bracket at name underscore p, and this is referring to the geometry that's coming from the attribute promote over here, is not equal to prim1 comma quotation name close quotation comma 0. Okay, close the brackets, and that will be our conditional statement. And inside we'll be giving this expression remove point bracket 0 comma at ptnum. So here we have an expression that will basically remove all the points from the proxy mesh, depending on not whether the piece number from the attribute promote is not equal to the piece number from the assemble node. We also need to enter code for the deform attribute triangle, and we can just copy paste the same exact code over here. So basically what we are telling Houdini here is that we want to read the attribute name from the primitives that's coming into the first input port. So that's how we read attributes which is being imported. And if we have done everything correctly, it should separate our high poly pieces into their own individual pieces, and will not get those stretched artifacts. And that's how we project high poly mesh to a fractured low poly simulated proxy geometry. So now we can export it. So we can do that by adding an ROP Alembic node if you want to export it out as an animation. And in the Alembic node, what we can do is that if we middle click on the node, in the for each node, if we middle click on the node, we can see that we have some point attributes. We have some primitive attributes that we don't really need. That is the name and the path. So what we can do is we can add in an attribute delete. By doing that, we'll basically reduce the file size of our Alembic file. So I can just click on that drop down arrow and choose these names. And if I just middle click on that, we see we no longer have those attributes. We can go back into the ROP Alembic, and we can choose render frame range, and you can give it a custom frame range. So for now, since I already have it pre-rendered till frame 6, let's say, I'll just enter it from 1 to 6. So you can go higher, obviously. And in the Alembic file output, we can click on that icon over there, and can save it. I'll type in file.abc. Make sure the ABC extension is there at the end so that you can export it out as an Alembic file. I'll click accept. And once we are done with that, once we are happy with it, you can click on save to disk. Okay, once you're in Cinema 4D, what you can do is that we can click on file and we'll click on merge. And what I'll do from here is that I'll go into my folder where I have saved it. Okay, so that's our mesh imported. Okay, so you can see that our pumpkin has some tags over here in the object manager. So if you had UV'd your mesh beforehand importing to Cinema 4D, we'll get that same UVs once we export it as animation. So you could use those same textures for texturing if you had any. Also, we'll get some selection tags, and this depends on whether or not you had made some groups in Houdini using the group nodes. This will be helpful also for texturing, and I'll just show you a quick demo of how to texture this. So I'm not even going to be using Redshift for this purpose. Most of you know that I use Redshift for rendering. In this case, I'll be using the standard Cinema 4D render. I'll not be even rendering maybe. So let me just apply that material over there. And if you have any, like as I said, if you have UV unwrapped this mesh before, you can use those same exact textures that you have. So in this case, for my pumpkin, it came with this color texture. And if I just import that, you can see that it still maintains the texture. See that if I render, you can see it clearly. If I play it also, you can see that it still maintains those textures. And using this already existing selection tags, we can, let's say we can apply another texture on top. And in this material, you can see we have a selection attribute over here. So we can just drag and drop the selection, whichever one we like. And depending on which selection tag you drag and drop, it will only apply it to those selections. So that's pretty much it. That's how you basically make a fractured soft body simulation in Houdini using Vellum. If you found this tutorial helpful and learned something new, consider supporting me on Patreon. I usually post all my scene files there and my Houdini digital assets, as well as some quick tips. So if you have some questions or doubts, you could comment them down below. I'll try answering them. So that's pretty much it, and I'll see you in my next tutorial. Take care.